In this lecture, we introduce the fundamental principles of quantum computation from the geometry of a single qubit to the concept of universality. The goal is to understand how quantum gates combine to perform arbitrary computations. We begin with qubits and the Bloch sphere, then study single and two-qubit gates. Next, we introduce controlled operations and gate approximation. Finally, we show how these elements lead to universal quantum computation. A qubit is a two-level quantum system with states 0 and 1. Its general state is a superposition, and physical states are rays, not vectors. A qubit is therefore a point in projective Hilbert space. The projective space of a qubit is a sphere, the Bloch sphere. Measurement collapses the state to 0 or 1, yielding one classical bit. Quantum evolution corresponds to rotations of this sphere. Classical logic gates act on bits and are often irreversible. Quantum gates act on qubits through unitary transformations, so they are always reversible. Physically, a quantum gate is a rotation of the Bloch sphere. Poly X acts as the quantum NOT gate, while poly Y and Z generate other basic rotations. Phase gates add relative phases, and the Hadamard gate is special because it changes basis from computational to diagonal. Together, they allow full control of a qubit, giving access to all of SU2. In classical logic, only NAND is universal, while XOR can be made reversible. The CNOT gate lifts reversible XOR to quantum mechanics. It uses one qubit as a control to flip another, and it is the simplest gate that creates entanglement. The CNOT gate is a controlled X operation. Controlled U is its direct generalization. The unitary acts on the target only if the control is 1. This is how quantum circuits implement conditional logic, entanglement, and algorithms. Controlled U operations scale naturally. A single control can trigger multi-qubit targets, multiple controls can be combined, and control on 0 is obtained by simple conjugation. This flexibility makes controlled U a fundamental building block of quantum circuits. Remarkably, any single-qubit unitary can be approximated arbitrarily well using only the Hadamard and T gates. Equivalently, the set formed of H and T densely generates SU2. With the Solovay-Kitev theorem, this approximation is also efficient. The gates H and T correspond to simple rotations of the Bloch sphere. By composing these rotations, we obtain a new rotation about a fixed axis by a specific angle. This composite operation is generated through the sequence TH-TH. The key fact is that this rotation angle is an irrational multiple of 2 pi. As a result, repeated applications densely fill rotations about the same axis. Any desired rotation around that axis can be approximated arbitrarily well. Rotations about a single axis are not enough to generate all of SU2. By conjugating with the Hadamard gate, we obtain a second rotation axis. Together, these two axes allow access to the full group of single-qubit unitaries. Any single-qubit unitary can be decomposed into rotations about these two axes. Each rotation can be approximated using powers of the basic irrational rotation. Because errors add linearly, the full unitary can be approximated to any desired accuracy. The Solovay-Kitev theorem guarantees that this approximation is efficient. The number of required gates grows only polylogarithmically with precision. Therefore, the gate set HT is efficiently universal. A gate set is universal if it can approximate any unitary operation. A standard universal gate set consists of single-qubit gates, such as Hadamard and T, together with the two-qubit CNOT gate. Universality follows from two results. First, any unitary can be decomposed into two-level operations, introducing only a controlled decomposition error. Second, each two-level operation can be approximated using single-qubit gates and CNOTs with a bounded implementation error. The total error is the sum of these contributions and can be made arbitrarily small. Any unitary acting on a finite-dimensional Hilbert space can be decomposed into two-level unitaries. Each acts non-trivially only on a two-dimensional subspace. Thus, universality reduces to implementing arbitrary two-level operations. A general multi-qubit unitary reduces to operations acting on pairs of basis states. These pairs are connected using gray codes, where successive states differ by 1 qubit. This localizes a global operation into simple transitions. The implementation of these two-level unitaries goes as follows. First, CNOT gates shuffle amplitudes along a gray code path. Then a single controlled two-level operation acts on the target qubit. Finally, the shuffle is reversed to restore all basis states. Universal quantum computation relies thus on reducing any unitary to two-level operations. Gray codes move information locally, CNOT gates reposition subspaces, and a single controlled operation performs the desired transformation efficiently. In conclusion, quantum computation is fundamentally geometric. Qubits are points in projective space, gates are rotations, and universality arises from combining single-qubit control with entangling operations. Through controlled approximations and error management, any unitary transformation becomes physically realizable.